In this video, I will talk about the capacitance of a spherical conductor. We'll measure a capacitance of a spherical conductor. So let's say you have two spheres. This is a solid sphere and this is the hollow sphere. Inside this red sphere, we have another sphere. And let's assume the amount of charge onto each sphere is minus q and plus q. So these are the charges onto the sphere. The radius of the sphere, the inner sphere is a and the outer sphere is b. And as you know that the electric field is always from positive to the negative. And also the electric field is always perpendicular to the surface. What does that mean? That means the electric field is perpendicular to the surface and goes from positive plate to the negative plate. And at this point, the electric field is also perpendicular to the surface here. Okay. The electric field inside a sphere is zero. And why is that? Just by the Gauss law, if you create an imaginary Gaussian surface, so and it does not include any charge, so there is no any electric field because there is no any charge enclosed. If you want to recall, just go back and take a look at the Gauss law. Okay, and there is no any electric field outside as well. The total electric field is only between the two spheres. And now we are interested in finding out what is the potential difference between the two spherical conductors. So, and this is the formula for calculating the potential difference between the two conductors, where E is the electric field at any points, okay, and dr is the displacement. The electric field, so this is the direction of the electric field, and the direction of the displacement is also in the same direction. So the electric field and the displacement are in the same direction, so both are parallel. So this dot product can be given by E times dr now, because there is no any angle between them. If there were an angle, then you had to write down the cosine component as well. Remember, the cosine, the dot product is defined as A dot V vector is AB times cosine theta. In this case, theta is 0. And we are finding out the potential difference between the two plates. So we have to integrate from A to B. That's what it is. From A to B. And this E is the electric field at any point between the two conductors, any point. And if I look at the Gaussian surface or any surface in between, then for this sphere, this one just behaves like a point charge. And you can also recall it from the Gauss law from the previous chapter. And the electric field at any point within the two between the conductors is given by kq over r square. So this is the electric field, and this electric field is between any points within the or between the conductors. And q is the charge onto the inner spherical conductor. Okay, k is a constant, q is a constant, so I'm just taking out. Then we have 1 over r square, and if you do the integration of 1 over r square, you will get negative 1 over r. Okay, so I'm just putting 1 over r, and this negative will make it positive. So what we have final relation is VB minus VA, that is the potential difference, is now equal to KQ over 1 over B minus 1 over A. Or further if I further simplify this one, then this is what I get. KQ A minus B divided by AB. So this is the potential difference between the two spherical conductors. Now if you go by the definition of a capacitance, the capacitance is defined as a charge per unit with potential difference, or the magnitude of the potential difference, VB minus VA. So now if I just plug in this equation 1 into equation 2, okay, Q, and then I'm just plugging the VB minus VA from this equation into here, then what you get is the capacitance is AB divided by KB minus A. Again, the capacitance does not depend upon the charge. It does not depend on the potential difference. It only depends upon the geometrical parameters. In this case, the geometrical parameter is the radius and the medium between the two conductors. Okay, so that is determined by K here. So AB divided by K divided by B minus A. What does this equation tell you? You can increase the capacitance by decreasing B minus A, or by making the gap smaller. There are two ways you can make the gap smaller, either by decreasing B or by increasing A. If the two conductors are very close, then there will be more capacitance, or if the distance between the two conductors is small, then the capacitance will be bigger. Okay, that's what this equation tells you. Now let's take a look at a special case. When I say a special case, that means in this case what we're going to do is, if the outer conductor, if this conductor is very far from the inner conductor, or in other words, let's say if you have only one conductor, then what is the capacitance? If we have one conductor, then we can assume the other conductor is very far. A spherical conductor is very far from it. So if you have one conductor, then we can assume the other conductor is very far. Okay, in other words, now we are going to find out the capacitance of an isolated spherical conductor. Okay, how are we going to do that? So we start from this equation, and then I'm just simply simplifying this one, just keeping A and then dividing this equation by B. If I divide this equation by B, what I will get is this equation, or in other words, B divided by B will be 1 minus A over B. So this equation and this equation is exactly the same equation. Now if B tends to infinity, what does this mean? That means if the outer conductor is very large, if this conductor is very great, then what I will get is C is equal to 4 pi epsilon naught times A, or A over K. This is A, and this term infinity, this will be infinity, and A over infinity will be 0, and we are left with A over K. Okay, because if B tends to infinity, this term will be 0, and we'll have only A over K. And as you know that K is equal to 1 over 4 pi epsilon naught. K is equal to 1 divided by 4 pi epsilon naught. I think I forget to put 1 over 4 pi epsilon naught. So this is the capacitance of an isolated sphere. Okay, so what you can see here, we can increase the capacitance by increasing the radius of the sphere. And again, this quantity, if you look in order to just make the 1 farad capacitor, you need a much bigger radius, and I'll talk about in the next video. So this is the equation for an isolated a spherical conductor, and this is the equation for two concentric spherical conductors. Alright, again, if you have any questions, write down your comments in the comment section, and do not forget to subscribe my channel. Thank you so much.